In this section, we'll look at how to use linear programming relaxations to get kernelizations for problems that we've seen before, and indeed better kernels or smaller kernels than what we've achieved with our more ad hoc reduction rules before. And we'll revisit our good old friend vertex cover. Remember, it's one of those really well-studied FPT problems. It is an FPT. You can easily get a 2 to the k search space algorithm. We could actually get down to something 1.3 to the k. That's not a result I've shown you in detail, but we could get, I forget what it was, 1.4 something. Was that the 1.6 to the k? Well, this was the best result that I only cited in the previous unit. So we know this is, from the perspective of fixed parameter tractability, is a relatively tame problem. But let's look at it again from the kernelization perspective. The best thing we had was a quadratic kernel. So given an arbitrary graph and this parameter k, what is your threshold for the size of a vertex cover? We could use this high degree rule, so just from removing every vertex of degree greater k, we could get the graph shrunk to something of size k squared at most. So we'll see something slightly better here now. First of all, let's rewrite it as an integer linear program. For vertex cover, that's also very easy. We have a variable as before for each vertex. Is it part of our vertex cover or not? Here we try to minimize the number of vertices that we have to pick, but then the constraint is for every edge, we have to pick one of the 2 vertices. I guess the formulation as integer linear program, again, makes even more explicit why vertex cover and independent set are so closely related. You almost see it immediately that they're kind of opposites of each other. Right? Remember, independent set was the same structure. It said maximize the number of vertices you pick, and the constraint was, okay, let's use UV here, was at most 1, except as opposed to greater or equal 1. So they're really kind of doing opposite things. Okay, but that's beside the point, just because we talked about independent sets a moment ago. So forget about this, focus on the integer linear program for vertex cover. Now again, that's a precise representation of the problem, but we cannot solve integer linear programs faster than the original problem. So instead of this, we consider the relaxation. So we just get rid of the integrality constraint, or more precisely, we replace it with inequalities. And we don't need the upper bound of 1 here. It's enough to constrain the variables to be non-negative, just because the minimization already makes sure that using anything more than 1 is never going to be an optimal solution. So that's another kind of trick here. It's a general approach that you'll see in many places, and it sometimes makes things magically more approachable, the resulting linear programs. So we essentially grow the feasibility region. But in a way that we don't get any new optimal solutions. Let me write the set of optimal solutions as well. because sometimes this is relevant. Usually we want to grow the region in a way that we never make any new optimal solutions. So we take that linear program, minimize the sum of xv, subject to the sum of two endpoints of an edge being at least 1, and all variables non-negative. And throw that into your favorite LP solver. You'll get some solution back. You can prove that it will never have variables set to a value larger than 1. And they will all be between 0 and 1. And they will satisfy the constraints, but they might be fractional. And specifically, we'll get some. So let's write this down, even though I just said it. It will be between 0 and 1. Whatever this optimal solution will be, I have to change that. Imagine that's a bold X instead of X with an arrow. Whatever that solution will be, we can define 3 sets of vertices now, depending on what their value, their variable has as value. There might be some that have exactly value 1/2 in the optimal solution. And those are in this set V0. And the other 2 are either below 1/2 or above 1/2. Okay? Now the claim is we can take these 3 sets, again, maybe say, what's a good mnemonic for I and C? I don't remember what I thought about when these were named. Well, I is inferior, so it's less than 1/2, and C is somehow the ones above 1/2. The claim is you can, without loss of generality, always take the vertices in C0 as part of an optimal vertex cover. And you never need to take any of the vertices in I0. And then, of course, there's the ones in V0 left where we don't know. But we'll see that we can essentially restrict the input to just those vertices in V0. And that's going to be the hard part of the problem. In other words, the kernel of the problem. And you can bound the number of vertices that are in V0. And so if you take a step back, like what have we done? We take our vertex cover problem, we write it as an ILP and take the relaxation. So far, so standard. And now we get some optimal solution back, and we can just, from the optimal solution, learn a lot about potential optimal vertex covers, and in particular, how big an optimal vertex cover is. I still find that somewhat surprising that this is this kind of detour via LPs gives you so much direct information about this graph. So let's prove this and kind of demystify what happens here. So we'll first prove this claim 1. And then the second part is actually not that hard. So the thing is that the statement here, to be precise, it only says there is some minimal vertex cover that contains all of C0 and nothing of I0. There might be other optimal solutions. So when we start, we assume that S is some optimal vertex cover. The goal will be to show that we can modify S to satisfy, we call that one S star. We can modify S star to be like the S in the claim without making it bigger. Okay? So we define the modified solution where we take S star, we take out all the ones that are in I0, and then we add everything in Z0. And we claim that's as well an optimal vertex cover. And that claim has two parts, right? It needs to be a vertex cover and it needs to be optimal size. But let's rewrite this first. We can essentially rewrite this as this. So where now Si is all the elements that are really in S. So, sorry, S star. Here I'm taking out an unknown number from I0, so I'm just giving that a name. All the elements in I0 that are in S star, these are the ones I want to not have in my solution to satisfy the claim. And conversely, this S bar C is everything in Z0 that's not in S star already. So part one is S is a vertex cover. Let's try to prove that first. When we add more vertices from this SC bar, we will not uncover any edges. So the only potential problem could be the vertices that we remove, right? These are certainly the only ones we have to worry about. So suppose we have such an edge. And say V is in I0. By definition, I0, these were the vertices where the corresponding optimal solution of the LP had a value less than 1/2, right? So XV star was less than 1/2. But the solution has to satisfy the constraints, so the other endpoint has to be strictly greater 1/2, which means this W is in Z0 by definition of that set, which means we'll eventually include W for sure. So we might remove V0 if it even was in the solution S star. But even if we remove it, we make sure that we add back in the other endpoint, so that edge will be covered. Okay? And that's basically all. Any other edges we don't touch. If it has no endpoint in V0, whatever endpoint it previously had in S star, it'll still be there. We don't remove it. So that proves that our constructed set S is indeed a vertex cover again. That's good. Then we continue here with the claim that the size of S is the same as the size of the optimal solution, which means it's also an optimal vertex cover. And the way we've rewritten our construction for S, so here, so the dot above this union here means disjoint union. It's just a way to express that I kind of know that the two sets will be disjoint. There's no notation for disjoint set difference, but if there was one, it probably will be a backslash with a dot above. I don't know, right? So what I'm saying here is this is also a disjoint set difference, which means, I mean, this is of course nonsense. A set difference for disjoint sets wouldn't do anything, but we're not. There's nothing in this set Si that is not in S star. It's kind of you're taking the set difference where the set you subtract is a subset. Okay, let's doesn't hurt to write it down. That was the idea of the construction. I guess I said it maybe verbally, but Si is a subset of S star, whereas the SC bar is disjoint from S star. So to say something about the size of S, you can take the size of S star, you subtract the size of Si, and then you add the size of SC bar. So let's do one more step here. So the size of our S, stay here. The size of our S is the size of S star minus the size of Si plus the size of SC bar. Okay. Follows just from this. So it suffices to show that what we subtract is at least as much as what we add. So let's try to do that. We'll have to somehow use the properties of these sets. And I mean, the intuition here is both of these are only talking about vertices where the value in the optimal x was not 1/2. It was strictly bigger, respectively strictly smaller than 1/2, which means you can take these variables and change their values a little bit and see what happens. Okay, so let's define some little epsilon, which is the smallest slack you have between any of the xv's in Z0 and 1/2. So what's the minimal difference any of these has from 1/2? It's got to be non-zero, because these are just some real numbers, and we define Z0 to be all the vertices that have a value strictly greater than 1/2. And so now we'll define some new vector, which is the same as x star, except for some entries. So when we have a vertex in Si, then we set this, let's call this x prime maybe. We set x prime for that vertex to be the old value plus an epsilon. And for the vertices in SC bar, we subtract the epsilon. And we know that this leaves the value at least 1/2 still, because epsilon was chosen so that for all of those there's more than that of slack. Yeah, epsilon is greater than 0, but then the difference is greater or equal 1/2. Okay. And the claim is that this still fulfills the constraints. which means we have to check that for every edge, this is true. Okay, maybe I'm running out of space here. Now, where could this be violated? It's an inequality, so it's only going to be a problem if I make variables smaller. So it'll only affect edges that have some endpoint in SC bar. Okay. And this was C0 without our S star. Let me continue on the next page for this. Now, if the other endpoint was in this set, IS, SI, no, it's not our SI. So in that case, W is not in S star. Because it's not removed. All right, so sorry, I think this is V. I've changed names here. So let's say the vertex that we look at is V. That's the one you could only violate this constraint for an edge where one endpoint is among those where we subtract something from XV. That must be in SC bar. And so we distinguish cases where this vertex could be. And suppose it was in this I0 without S star. But then we don't have this in S star. Why do we also not have the other endpoint in S star? I'm not sure anymore why this follows. Yeah, sorry, this must be the other endpoint. So we have one endpoint in SC bar. Then we distinguish cases for the other endpoint. It still follows now for both, because both vertices are in some set where we subtracted SC star. So if they were in SC star, they would not be in this set difference. All right, so that's true for V because of the assumption here. And it's true for W because of the case distinction. So if V is in SC bar, it cannot be in S star. That's why V is not in S star. If W was in this set I0 without S star, then it would also not be in S star. But then S star cannot be a vertex cover because there's an edge VW that's not covered. So that case cannot actually be true. What other options do we have? We could have that W is in Si. In this case, it's one of those where we increment the variable by epsilon. All right, so x prime W is x star W plus epsilon. And so if you sum up the two, you satisfy the constraint. It's just the same as the old. They have a plus epsilon and a minus epsilon. And that was greater equal 1 because it was an optimal solution. Okay. So then the third case is that W is not in I0. This was in I0, but not in S. This was in I0 and in S star. And now we have the case it's not in I0. That means its value is greater or equal 1/2, because it either was before or even further increased it, but it certainly it was not in this set I0. So previously, it had a value of 1/2, and we don't subtract anything from it. And for our edge here, we subtract something, but we leave that above 1/2. That's this property. So if both are 1/2, then the sum is at least 1, right? So in all possible cases, for the other endpoint of an edge where we might subtract something from its variable, the other endpoint makes up for it, or the case is not possible. And so we've proven that this new x prime indeed fulfills the constraints of the LP. Now, what do we get from that? Because X is an optimal solution of the LP, we get that the sum over all vertices in the new solution we construct cannot be smaller. And if you rewrite this, the definition of this xb prime, this entire sum here, we sum over all the vertices, and then it's the original xv, and then we have epsilon times something we subtract and something we add. So if we go back to the part here, what do we add? Well, we add epsilon for every vertex in Si. And we subtract something we subtract epsilon for every vertex in SC bar. And epsilon was greater 0, right? So if you take this chain of inequalities together, it means that this difference must be at least 0. And so that means we've proven what we claimed here. It suffices to show that this SC bar is at most SI. That's the end of part 1. Okay? We've shown we can take an arbitrary optimal Z cover. We can transform it into one that satisfies the conditions from the theorem, namely include all the vertices where the variable is strictly greater than 1/2, and get rid of all the vertices that have values strictly less than 1/2, and the result is still an optimal vertex cover. Which means we can essentially assume that we fix this solution and just look at the remaining vertices, namely those with V0. So the second part of this theorem claims we have an induced subgraph where we only look at the vertices in V0, and we have to subtract from the threshold the vertices that we include for sure, namely those in C0. And then that is a valid kernel for the original input, and its size is bounded. Okay? So let's see that, and I need another page. So, check. For claim 2. First of all, we know the LP objective value, which, what was that again? It's the sum of the XV stars, right? Is never worse than the ILP objective value. That's what we used before. Now, the ILP objective value is the size of an optimal vertex cover. That's greater or equal than this thing. Sum of all vertices. And what we're going to do now is look at, so this is also true like for any graph, right? This is for any input to the vertex cover problem, this is true. So what we'll do is we'll repeatedly apply the following reduction rule. You take the LP relaxation of the vertex cover problem. That gives you some optimal solution X star. And from X star, you get these sets I0, I0, V0, C0. You remove or delete all vertices in I0. Include in solution all vertices from C0. And repeat this whole thing. So in each reduction step, we get rid of every vertex in I0 and C0. The only difference is that we keep track of the deleted vertices in Z0 because they will become part of the final output solution. And we're left with the V0 vertices. I think it's hard to prove whether one round of this reduction is enough, but we can just pretend we apply this reduction as long as we still get vertices where the optimal fractional value is not exactly 1/2. Okay? So after this, we'll have x star v is 1/2 for all vertices in our remaining graph. And let's call this v0 as before, was defined like that anyways. At this point, what did I do? I think I zoomed. At this point, we'll invoke this inequality from above. And now we know exactly what this sum is. It's 1/2 the size of our vertex set, because every vertex has value 1/2. Okay? So what does that mean? It means the optimal vertex cover needs to pick at least half of the vertices in my graph. So there's two options now. If we have more vertices in the graph than our parameter allows, then we're doomed. We cannot possibly pick a vertex cover from those. There's not enough, our parameter restricts us too much. Okay, then we can, in terms of a kernelization, you output a no instance. And in the other case, means we don't have a lot of vertices. And so we get a bound on the number of vertices in the kernel. Okay. That's the end of this part. This shows how you can use an LP with a bit more sophisticated analysis to get a stronger reduction rule. One that doesn't simply use these local arguments we've done before, like just the degree of a vertex, but a more global picture, because the LP is really taking the entire graph into account.